All right, so we're going to talk about forces that act on aircraft. So there are four forces that act on an aircraft. They are lift, drag, weight, and thrust. So we'll talk about each one, how they work, and what direction they go in. So there are these four forces are defined here on this slide. So let's look at each one. So let's start with weight. So we can see that weight always acts in the downward direction towards the Earth. All right, so it's the attraction to the Earth that we typically call gravity. So whenever you're thinking about weight, think about gravity. So it's the force of gravity that acts downward. We call that weight. Lift is the force that opposes gravity. So we can see up here in the corner that weight goes down, where gravity pulls us down, and lift pulls us up. All right, so lift is created as air passes over and under the wings. Now, lift can be created in other parts of the aircraft too, but typically we think about lift created as air passes over the wings. Thrust and drag are the last two forces. Let's look at those a little closer. Thrust propels the aircraft forward, while drag sort of pulls it back. It's this tug of war that happens between thrust and drag. So a lot of aircraft have engines that thrust it forward, and the shape of the aircraft, along with the air that's kind of interacting with it, create this drag force that limits our thrust. So these four forces work together to create kind of the experience that we have when we fly aircraft. Weight and lift oppose each other. Thrust and drag oppose each other. And they're kind of in these two tugs of war, thrust and drag and weight and lift, to create a stable flight for our aircraft. Let's talk about that tug of war a little bit more. This is a little bit of physics stuff that we're going to go into. So in physics, when two forces are applied to an object, you can imagine this object as the plane, right? So this is the object we're talking about. When you have two forces that are applied to an object, what you can do is sort of subtract one from the other, and sort of like a tug of war. So in this case, we have two forces. We have a 75 Newton force. Newton is the N there. That's just one way to measure force. So 75 newtons is one force, and that's in the left, or to the direction to the right. And then on the direction to the left, we have a 40 Newton force. So when we take 75 newtons and we subtract 40 newtons, we end up with a result of 35 newtons in the forward direction. So that's just what's being shown here. And all you got to think about is if you had two teams in a tug of war and one team was pulling at 75 newtons, which is a way to measure force, and the other team was only pulling with 40, well, which team is going to win? The team over here is going to win. And the object, which is the rope, is going to kind of speed up in this direction towards the winning team. So you can imagine that this sort of scenario will happen with any kind of object, but we're focused on aircraft. So this happens with aircraft as well. Before we get into the aircraft portion of it, what happens if both forces are equal? So what ends up happening here, if we had like a tug of war and both of these forces pulling on the object, which is a rope, I guess, or any object really, are equal, we would have 465 to the right, 465 to the left, and we end up with a 0 overall force. So you can use math if you want to, 465 minus 465, and we end up getting 0 as our total result of our tug of war. So we call that 0 result a resultant. So that's just what we call it. The resultant force is going to be 0. So if there's a tug of war, both teams are pulling with the same amount, this object, which is the rope, is not going to move is not going to speed up in either direction, to the left or the right. So what this is called, when an object is sort of like in the midst of a tug of war with equal forces on each side, we have a special term for it. That special term is called equilibrium. So if the resultant is 0, we say that the object is in static equilibrium. All right, so kind of equal on both sides, right? Equal force on both sides. So there's two things that we can apply to this object. Either the object is not going to be moving. Think of like a tug of war rope, probably isn't moving at all. Or it could be moving, but not speeding up or slowing down. All right, so that's kind of the two scenarios when you have a resultant of zero for our forces when you add and subtract them to one another. Either the object's not moving, or it could be moving, but not speeding up or slowing down. So let's look at two scenarios where we have objects that are in equilibrium, where the resultant force is 0. The first one is this tug of war over here. So we just mentioned that a little while ago. So in a tug of war, let's just put some phony forces on here. Let's say that we have one force of 50 newtons, and we have to the left, and to the right, we can say we have a force of 50 newtons, right? So in this case, what's going to happen? This rope is going to be in equilibrium, and probably it's not moving at all. So that's one scenario if it's in equilibrium. So we'll put that the rope is in equilibrium, and it's not moving. All right. Now let's look at the other scenario over here. This is a car. Now we're going to say that this car is moving. All right. So I'm going to put little, like, I don't know, whatever these are, yellow lines to indicate we have a moving car. But I'm going to say that this car is also in equilibrium. So we're going to say is we have two forces. One force is pushing us forward. We'll call this force the force of the engine. All right. So the engine provides some force to push us forward. We also have a force in the other direction, and the other force is called drag. We talked about drag earlier. Airplanes also, or aircraft also experience drag, and it has to do with the fact that it's the car is experiencing like this air that's kind of slamming into it and moving around the car. So what ends up happening, let's just say that the drag force is 100 newtons. We'll also have a force of the engine 100 newtons. But this car is still moving, right? We put these lines here to indicate the car is still moving. But I like to think of this as the car is in like cruise control, all right? So if you've ever, I don't know, most of you haven't driven a car, but you might have heard of cruise control. When you're in cruise control, that means that the engine provides enough force so that the car on the highway stays at the same speed. So it doesn't speed up or slow down, right? And what we do is the car is experiencing this drag force, and we, as the car's operator or the cruise control, applies just enough force to make sure that the overall resultant force is 0. So the car is actually in equilibrium. So we'll write that down here. We'll put 0 resultant force. We'll also write that the car is in equilibrium. So this car is not going to be speeding up or slowing down, because the force going to the right is the same as the force going to the left. So this car is not stationary. This car is moving, but we have two forces that are acting on it that's keeping it at the same speed. So just like the last slide, when the resultant is 0, the object's either not moving or it's moving, but it's not speeding up or slowing down. All right, so let's look at thrust and drag in terms of an aircraft. So thrust is the force that propels our aircraft forward, kind of like the force of the engine with the car. And drag limits the forward speed, I guess, the forward kind of acceleration of the aircraft. And when force and thrust are equal, what do we have? We have equilibrium. Just like the car in cruise control, this aircraft will not be speeding up or slowing down. It'll stay the same speed, which is kind of nice. If you're inside of the aircraft, you don't want the aircraft to be constantly speeding up or slowing down. We really like it when thrust and drag are the same force, because when that happens, our aircraft doesn't change velocity. It just keeps staying the same speed. Now there's another scenario when we can talk about if we wanted to speed up the aircraft, we would increase the thrust. If we wanted to slow down the aircraft, we would decrease the thrust. And that's kind of how you speed up and slow down in the air. You make the thrust larger or smaller. Now with gravity and weight, we have this other tug of war happening, but in the other direction, the up and down direction. So weight is the downward pull of gravity, and lift is the force that kind of opposes, it goes in the other direction of the weight. Remember from earlier, the lift force is created as air flows over and under the wings. We'll talk more about lift later. But just for now, know that the force of lift keeps us in our aircraft from accelerating downward. As long as we have that tug of war, that equilibrium, our plane does not dip up and down. It stays at the same altitude, which is nice. Once again, if you're in a plane and you're flying in a plane, you want the lift and the weight to be equal most of the time. Unless you wanted the plane to go upward, we would increase the lift. If we wanted the plane to go downward, maybe to land, we would decrease the lift a little bit so that it would speed up downward. So most of the time in a plane, we want all four, the drag and the thrust to be the same. So we're at a constant velocity. We want the lift and the weight to be the same. So we're not moving up or accelerating up or down. If you have these forces kind of in equilibrium, our plane is very stable and doesn't move around a whole lot, and it's more comfortable for the people flying the plane or passengers in the plane. So those are the four forces of flight: thrust, lift, weight, and drag.